Okay, guys, if you've been watching the previous videos, then I'm sure that you've been working out some problems, and you're very familiar with continuity means by now. And this is going to be a breeze to understand this, or at least by the end of this video, I hope it is. Well, what this theorem says, it's a very valuable theorem, and it's going to tell us some good results once we work out problems. You'll see how valuable it is. But what it says is if we have some function that's continuous, a function f that's continuous on a closed interval like the one we have here, and k is some number between f of a and f of b, then there's at least one number c in the interval such that f of c is k. Now all of that sounds a bit like nonsense right now, but let's talk about it then. I'm sure it'll sound better real soon. So what this means is if it's continuous, and in this case we're going to assume that it is, it seems to be right, there's no holes, no breaks, no gaps, and k is a number between f of a and f of b. So we should put together where f of a is. F of a is this value right here. Okay, so the function evaluated at a, it'll give us our y point, and f of b is approximately right here, right? So function evaluated at b, and k is a number between f of a and f of b, so it's got to be somewhere here. For this example, it could be anywhere, as long as it's between f of a and f of b, as long as it's between here and roughly here. So this will be okay. So this is our k value here. So then there's at least one number c in the open interval, c, such that f of c is k. Well, this is c, and what we're saying is that this number exists if these conditions are met. So f of c is equivalent to k. This is really the big result. And what this is going to help us find is interesting things. For example, if I have a function such as maybe one that looks like this, and I ask you guys, how can you show me that there are zero, that there's at least one zero here? Well, you're going to tell me, look at this. There's our interval, right? Our closed interval here, a and b. Here's our f of a, right? We need to define these. Our f of b is over here. Now, what our theorem tells us that k, some number between f of a and f of b, so we could say, okay, it's maybe right here, somewhere. Here's our k. And there's now the theorem guarantees there's some c such that this point is such that k is f of c. And that is true. So the interesting thing about it is if I told you, all right, prove to me that there's at least one zero in this function. The thing is that f of a, and according to this graph, we don't know it algebraically, but we're going to work out examples in the upcoming videos, and this will become much more clear. So I hope you guys stick around if you don't understand this, or replay the video. But f of a seems to have some negative value. So we're going to say it's negative. What letter do you guys like to use? This is negative alpha. And f of b is going to be some other number. Okay, it's definitely going to be different. So we'll say it's going to be positive. So we'll say positive beta. What's interesting is that from f of a to f of b, we have sign changes. Notice this. Positive, minus, and a positive. So what this means is, our theorem tells us that this function is, if it's continuous, and it is, and there's some k in between, and all the conditions are met, and the signs are different, f of a and f of b That's right. Have different signs, there is at least 1 0. And it's somewhere here. This could be the mystery point. It could actually be the k that we were talking about. We don't know because this is an example with just parameters, and we're gonna make sure I work out real good ones in the coming videos. But stay tuned. Go over this video to absorb the theoretical aspect of it. I think this is much better with examples personally, so I'm gonna give you guys a lot of them and follow examples. I promise you guys you'll understand this. This is a very important thing to get. So stay tuned.